The topic is AVL trees. These are height balanced binary search trees. How the height of a tree is balanced? It is balanced using balance factor. Balance factor is height of left subtree minus height of right subtree. Balance factor is height of left subtree minus height of right subtree. In short, I can say that balance factor is height of left subtree minus height of right subtree. So this balance factor we calculate on every node of a binary search tree, or now we will call it as AVL tree. On every node we calculate this. And the balance factor of every node must be either -1, 0 or 1. It should be any one of these. These are valid balance factors. So if I take mod upon this one, mod means absolute, right? Mod is absolute. So this absolute value should be less than equal to 1. Means that -1 also you take it as +1, right? Mod means +1. So the balance factor should be, absolute value of balance factor should be less than or equal to 1. If balance factor of any node is greater than 1, then that node is imbalance. If it is less than or equal to, then the node is balanced. If the absolute value of balance factor is less than or equal to 1, then the node is balanced. If the absolute value of balance factor is greater than 1, then the node is imbalanced. So we calculate balance factor for each and every node in a AVL tree. Every node should be balanced. If any one node is imbalanced, then we say tree is imbalanced. So how to balance that tree? We perform rotations for balancing that tree. Alright. So first of all, we will learn how to calculate balance factors. Let us take some example trees and learn how to calculate balance factors, how to identify a node is balanced or imbalance. I have some example trees. Let us find out balance factor for each and every node in a tree. So first I will select this tree, this one. Balance factor of this node is height of left subtree minus height of right subtree. What is the height of left subtree? 1, 2. 2 edges are there. Actually, height of left subtree means from here I should see the tree. Now what is the height? 0, 1. Actually height is 1. Then what is the height of this one? This is also 1. But I did not take 1, I said 2 because I counted edges. So 2. This side also I will count edges, 2. So I am getting 2, 2. So answer is 0. Anyway you take 1, 1 or 2, 2, it's the same. So for finding the height you can just count edges, or else you can take the levels also. So you should do the same thing on every node, right? Make sure whatever you are doing, you do the same thing on every node. Let us take the balance factor of this one. Height of left subtree is 1. Height of right subtree is 1 edge. 1 minus 1, 0. This nothing is there, so it is 0. 0 minus 0 is 0, right? This is 0. This is 0. What about this? 1 on left side and a 0 on right side. So 1 minus 0 is 1. So the balance factor is 1. So 0, 0, 0, 0, 0, then 1. Let us calculate for this one. This is 1, 2 minus right side 1, 2, 2. So this is 0. Then here I will write the direct value. This is 1 and 0. 1 minus 0 is 1 and this is 0 only. This is 0 only. This is 0 minus 1 is minus 1. What about this? Let us put the values first on leaf nodes. Then for this 1, 2, 3, 1. 3 minus 1 is 2. Oh, this is imbalance. This is imbalance. What about this? 1, 2 and 0 this side. So this is 2. This is also imbalance. And this one is 1 and 0. So this is 1. So you can see that there are two nodes which are imbalanced in this one. There are two nodes. Then what about this? Leaf node 0, 0. Okay. From bottom I will start. This is 1, 0. So this is 1. And this is 0 on this side. And 1, 2. So this is minus 2. And this one 1, 2, 3 on this side, 0 there. So 3. This is 1, 2, 3, 4 on this side and 1 there. So this is 4 minus 1. This is 3. This is imbalance. This is invalid actually. See one thing. In AVL tree, whenever you calculate balance factor, you will never get balance factor as 3. You will get a 2, okay, 2 is okay, minus 2 is okay. So you have just gone beyond the balanced tree, right? So 3 means that is too much. You will never get balance factor as 3. Alright, so that is not a proper. So that is invalid example. I'll show you why you will not get balance factor as 3. Then one more thing. Now one common mistake what students do is find the balance factor of this one. One node minus 1, 2, 3, 4. 4 nodes minus 3. You don't have to count nodes. You have to count levels or height, right? So 1, 1, 2, 3. So this is 3. So this is minus 2. Count the height, right? Check the height. Don't count all the nodes. Don't do this mistake. So I have shown you how to calculate balance factors. Now next, if any node is imbalanced, how to balance a tree by performing rotations, we will learn about it. In this video, we'll learn about rotations at the time of insertion. That is at the time of creation of AVL tree. When we are creating an AVL tree and inserting any key in an AVL tree, then some nodes may become imbalanced. So tree becomes imbalanced. So to balance that, we perform rotations. So those rotations are named as LL rotation, RR rotation, LR and RL rotations. We'll understand all these rotations one by one. So let us start with the first one. First one, LL rotation. Let us take a initial tree. Suppose this is an initial AVL tree. What are the balance factors? See, this balance factor of this is 0 and this is 1 and 0. So this is 1 minus 0 is 1. So balance factor of this node is 1. Then I want to insert a value 10. So after inserting 10 in this one, so where 10 will come? 10 is less than 30, less than 20. So it will come on this side. So 30, 20 and 10. What are the balance factors? This is 0. This is 1 minus 0. So 1. This is 2 minus 0 on this side. So this is 2. So this node became imbalanced. So the balance factors should not be more than 1. So but the balance factor is 2. So this node became imbalance. Now we will give the name for the imbalance. When this node became imbalanced because of insertion of 10. So in which direction that 10 is inserted? Left of left. LL. So I will give the name as LL imbalance. So this is LL imbalance. Now for LL imbalance, how to perform rotation? Let us take the tree once again here. So we'll perform rotation around this node. So we'll perform rotation in this direction. This direction. So what does it mean by rotation? Imagine that this is a thread. Okay, keep your finger here and pull the thread on this side. Pull the thread on this side. So if you pull the thread, it will rotate around this finger, right? So when it rotates around this finger, 30 will come on this side and 20 will move up at here and 10 will move little above its position. So the tree looks like this. This is the meaning of rotation. Hold your finger and move this node. So rotate around your finger, rotate around a fixed point. Okay. So this is the rotated tree. Let us check the balance factors. This is 0. This is 0. This is 1 minus 1. 0. All are balanced. So around which node we have rotated? This node. So at that place, who is there now? 20. Is it balanced or not? Yes, it became 20. Yes, its balance factor became 0. So on whichever node you perform rotation, the balance factor should become 0 for that one. Earlier, at that position, the balance factor was 2. Now the same position, the balance factor is 0. So this is the procedure for rotation. Now few important things. First thing, what should be the name of this rotation? Imbalance I explained, LL imbalance, right? So let us call the rotation also LL rotation. So I will give the name as LL rotation. So based on imbalance, I have given the rotation name also as LL. Now you can say that, no, it is rotating on the right hand side. We are pulling it on the right hand side. Call it as right rotation. Okay, that's also correct. Then somebody say that no, it is rotating like a clock, so it is clockwise rotation. Okay, call it as clockwise rotation. So you can give any name. There is no standard name for this one, right? This is just a rotation. There is no standard name. So if you want, you can give any name. I have selected the name so that it is easy for understanding even the complex things. So I'm calling it as LL imbalance. If I call it as right rotation or clockwise rotation, maybe I may not be able to explain you the things more clearly. Let us follow LL rotation. So this is after LL rotation. So this is about name. Now second important thing. You may be thinking that I have taken just a small tree just with the 3 nodes. What I should do if the tree is very big? So don't worry. Rotations are always done with 3 nodes only. Always done with 3 nodes. Even if a tree is having 1000 nodes also, rotation is performed over 3 nodes only. So understand this clearly. Then through examples, I will show you how it is done on bigger size trees also. So that's all about first rotation, right? Now next we will look at RR rotation. For RR rotation, this is the initial tree. Balance factor, leaf node is 0 and this one is 0 minus 1. So this is minus. Next, I will insert 30 in this one. So 10 and 20 are already there. So 30 is greater than 10 and greater than 20. So it comes on this side. Now the balance factor of this one is 0. This is 0 minus 1. So minus 1. This is 0 minus 2. So this is minus 2. Minus 2 is not a valid balance factor. Balance factor cannot be less than minus 1. This is minus 2. So this node became imbalanced. So why it became imbalanced? Because we have inserted 30 just now. Where we have inserted right child of right child. Right? It is the right child of right child. So RR. So let us call this as RR imbalance. Now let us see how to perform rotation. So I'll take a tree once again. Perform rotation around this node in this direction. So it means hold your finger here and pull this 10 on this side. So if you pull 10 on this side, then 10 comes here, 20 will take the place of 10 and 30 will move up little bit. Now the balance factor are this is 0 and this is also 0. So it's perfectly balanced. Now what should be the name of this rotation? As I said, this is RR imbalance. So let us call this as RR rotation only. So this is RR rotation. So this is after RR rotation. If you say no, this is left rotation, okay, you call it. If you say no, this is counterclockwise rotation, okay, you can call it. You can give any name you like. That's all. Now one important thing. In LL rotation, the final result was this one, previous rotation. And this rotation also same result. Yes, in all 4 rotation with just 3 nodes, we get the same result. That is a balanced tree. Now, next rotation we'll look at, that is LR rotation. For LR rotation, this is the initial tree. Let us insert 20 in this one. So, right now tree is having 30 and 10. 20 is less than 30, so it will come on left side. But it is greater than 10, so it will come on right side. What are the balance factors? This is 0. This is 0 minus 1, so minus 1. This is 1, 2 minus 0. So this is 2. 2 minus 0. This node became imbalanced. This is imbalance. Which direction insertion is done? Just now we inserted 20. On which side? Left, right. So left, right. First left child, then right child. LR imbalance. So let us call this as LR imbalance. And how the rotation should be performed? I will redraw a tree here. So first we'll perform rotation around this node like this. So what will be the result? 30, 20 and 10. Right? Pull 10. Holding a finger here, pull 10. 10 comes this side. 20 moves up. So this is how the tree looks like. The balance factors are 0, 1 and 2. Now perform rotation around this node like this. What is the result? Same old result. So 20 in the root, 10 and 30. See, pull 30 on this side, so 20 will move up, 30 will come down, and 10 also will move up. The balance factors are 0, 0, 0. What do you call to this? LR rotation. LR rotation. This is also LR. If you want to give the name based on the direction of rotation, just watch it. Left rotation, then right rotation. So this is LR only. With that respective also it is. So this is LR rotation. See, this is one rotation only, but there are two steps in this one. So we call this as double rotation. We call it as double rotation. Later I will talk about this one. This looks little complex, how to do this. So I'll show you a direct method for this one. Let us take this tree once again here. So this 30 should move this side, root should move this side, and this newly inserted node should go in the place of root. So 20 will flip on this side, right? It will come on this side. 30 will move towards right. 20 when it went on the root, 30 went on right side. So instead of two steps, we can see it as a single step. So you have to send this node there and move that node on right side. So that's all about LR. Then RL, I will explain you quickly. You have understood how these are working. For RL rotation, this is the initial tree, 10 and 30, right? Now we will insert a new element, 20 in this one. So if we insert 20, 20 is greater than 10 but less than 30. So it comes this side. Then the balance factors are 0, 1 and this is minus 2. So this became imbalance. Which imbalance? Right, left. So RL imbalance. So in short, I wrote RL imbalance. And one more thing, see, we get that result only, so that's why I did not remove it. We get that result only. Always we are getting same result for 3 nodes. Anyway, we have to perform rotation on this one. So I'll take a tree once again. Balance factors are 0, 1 and minus 2. Perform rotation over this node first. So 10 and at this place comes 20 and on right side it will be 30. So the balance factors are 0, minus 1 and minus 2. Then perform rotation around this node, we get that result. 10 is pulled down, 20 comes here, 30 also moves up. We get that tree. If you want to see a direct method, then this should be sent as a root or a parent and this should move on left side. So again, this is also double rotation, right? Because there are two steps. Actually, these are the steps, but for understanding, we take that one. So whichever you are comfortable with, you can follow that one. That's all about 4 rotations we saw. Let me write down the rotations we have seen. First is LL rotation. The LL or RR rotation, these are called as single rotations. These were having single step. And LR and RL are called as double rotation. But don't count this as 2 rotations. Count as one only. See, there is a difference between double and 2. So don't count them as 2 rotation. This rotation, if I take LR, it is 1 rotation. But it is having 2 steps, so it is double. Capacity is double, size is double, number of steps are double. Person is 1 only, but his size is double. So that's all about rotations. Now out of 4 rotations, I'll give you one observation that may be very useful for you. That may be logically useful for you. Observe this one. So out of 4 rotations, what is the observation? Look at here. So using 3 keys or 3 nodes, so I have 3 nodes, that is 3 keys. Using 3 keys, how many different binary search trees we can form? 5. How? 2n cn by n plus 1 number of binary search trees we can create out of n keys. So for 5 trees we can create. So what are those? How they look like? I will draw them. See, these are the 5 trees. Out of 3 keys, we can generate 5 different binary search trees. 2n cn by n plus 1. 5 are possible. What is the height? 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1. Oh, that is of minimum height. So 4 trees of larger height and that is of smaller height. AVL trees means height balance binary search tree. So which is more height balance? So when you have 3 keys, you can draw a binary search tree of any shape. All are binary search trees only. So if you have this one, why don't you take that one? Change this one to that one. How to change? We are saying that we are performing rotation. We are saying that we are performing rotation over this one, or double rotation, right? First on this one, next on this one, or double rotation, first on this one, then on this one. So actually we have transformed these 4 trees into that tree because that is height balance. And how we transform? We are saying that we have performed rotation. So this is the idea behind AVL trees. So idea originates from here. When you can have 5 different shapes, why don't you select that shape? Even if you got this one, modify it. Even if you got this one, modify it to that shape. So this is all about rotations at the time of creation, at the time of insertion. Next we will see the examples. If a tree is bigger, how rotation is performed. I'll discuss various things in that topic. So the topic is formulas for rotation at the time of insertion. So we have already seen 4 rotations. We have seen upon only 3 nodes. If there are many nodes in a tree, then how rotation should be performed? So for that we will look at a formula. So I'll show you only 2 formula, one for LL rotation, then LR rotation. Same thing applies for other 2. Let us look at first rotation. This is for LL rotation. I have taken an example tree. Only 3 nodes? No, it is having left child, right child. This is having right child, right child. Imagine a lot of nodes are there. So A is a root. No, imagine above that also a lot of elements are there. So where you are performing rotation? We are performing rotation upon this node who became imbalanced because balance factor is 2. Rotation is performed over this node. So we are talking about only 3 nodes. Maybe thousands of nodes are there in a tree. Imagine a lot of nodes are there in a tree. Alright. So now take it as a formula only with 3 nodes. If these are the balance factor, this is 2, this is 1, this is 0 means where the insertion is done, left, left, right? If this is -1 means it is LR, okay? This is LL. This is imbalance with the 2 means it is on left side. Then its left child is 1 means it is again on left side. If it is -1 means it's on right side, okay? With this also you can observe. Now finally, let us see rotation. Which rotation we are going to perform? LL rotation. LL rotation around this node, upon this node. Then what is the result? Who will come here? B will come here. Where A will go? On the right side. Then who will come in the place of B? C. What about rest of the nodes? C's left child and right child as it is. A's right child as it is. A's right child. Now who is missing? B's right child. See, this is on the right hand side of B and B has become root. Already right side A is there. Then where this B should come? It will be on the right hand side of B only, but it will become a left child of A. And after rotation, we know that the balance factors, all of them become 0, 0. Yes, for those 3 nodes. That's it. This is like a formula. So how this is working, I'll show you. I said that this is a thread, okay? So I'm keeping my finger here and pulling this thread. So if suppose something is attached to this thread like this, okay? Something is attached to this thread like this, like this. So if I put a finger and pull it on this side, then this will stretch like this and this will reduce, right? Then what about that thing connected? It will come this side. It will come this side, right? So whatever was here on this side, it will come on that side. Same thing, this BR was on this side, just it's like a thread, pull it, so this will come this side. So the effect is just like rotation. So that's why people who have developed this one, they have given the name as rotation because the effect is just like rotation. Let us look at example of LL rotation and apply that formula. As an example, I have taken a bigger tree with around 9 nodes are there. Now let us give balance factor and check whether everything is balanced or not. Let us give the balance factor for leaves. This is 0, this is 0, this is also 0, this is also 0. Then let us move up. So this is 0, right? This one 0, 1, -1. This is 1, 2, 1, 2. So this is 0. This one 1, 2, 3, 1, 2, 1. 1, 2, 3 minus 2. So 1. And what about this 0 and 1? Minus 1. So this is balance. Now I will insert a new value, that is 4. Insert 4. Key 4. Right? 4. 4 is smaller than 30. And also smaller than 20. Smaller than 10. Smaller than 5. So it comes here. So once it comes here, the balance factors along this path will update. So this is 0. What about this one now? This is 1, 0, 1. What about this one now? 1, 2 and 1. So this is 1. 2 minus 1, 1. What about this? 1, 2, 3 and 1, 2. So 3 minus 2 is 1. What about this? 1, 2, 3, 4, 1, 2. So this became 2. Yes, this node became imbalance. So here root node became imbalance, right? I selected the tree such that root becomes imbalance. Okay. Now we can see it perfectly. Who became imbalance? This one. Where the insertion was done from here, check it. Left, 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 left. Shall I say LLLL 4 times? No. You have to consider only 3 nodes or 2 steps. So what are those steps? These. Only 3 nodes. L, L. After this point, wherever it is inserted, it is LL. See, this came on this side. If suppose this was not 4, I have inserted suppose 6. So it will come this side. Then also it is LL. We have to see from this node just 2 steps. That's all. Which rotation will perform? LL rotation only. So I will draw a rotated tree here. So the rotation will be performed around this node. So here, so 20 will move up, and the place of 20, 10 will come. At the place of 10, 5 and 4 all will move. 5, 4 all will move, and 30 will move this side. So 30 this side, 40 this side, 50 this side. Now what about right child of 10? 10 is there now. Right child remains on its own place. What about the right child of 20? 20 became new root now. So this subtree of 20 will go on this side here. So what is there? 25. And along with that, it is having right child. Keep it as it is. Don't disturb anything. Just instead of linking here, it is linking this side. Because 20 has become a new root. This is the tree. Let us check the balance factors. 0, 1, 0, 0. This is 0. This is 0, 1, minus 1. This one 0, 1, minus 1. What about this 1, 2 and 1? 1, 2 and 1. So this is 1. This is 1, 2, 1, 2, 0. This one 1, 2, 3. 1, 2, 3, 0. See, the node over which we perform rotation, that should become 0, right? So this is a balanced AVL tree. So I have given you an example without 4, then I have inserted 4, then it became imbalanced, then I have shown you how to use that LL rotation for balancing. So you must practice this one by yourself, watch it again, watch this video again and pause it and do it by yourself. Next I will show you LR rotation formula. This is an example tree which will work as a formula for LR rotation. So already we have 3 nodes and one of the node is imbalance. It is a positive means it is left side imbalance, right? Then this is negative means this is right side imbalance. So this is LR. Assume that something is inserted below C, right? Not just C, under that node C. As I said, rotation is done only among 3 nodes. So this became imbalanced, so we'll just see 3 nodes. Now LR rotation. This is double rotation. We know the direct method that C will move up and A will move on the right hand side. So I will show it like that only. So C is coming here, B in its own place, A will move on the right hand side. Okay, perfect. What about B's left child? B's left child will be as it is. What about A's right child? It will be as it is. Now the problem is with the children of C. This is on the left side of C, this is on the right hand side of C. So CL will remain on the left hand side of C, CR will remain on right hand side of C. This is how the children will get distributed. Watch again here, C's CL, CR. So C became root. So CL on this left subtree, here right here this side, and CR on that side. So I'll take one example and show you. Suppose this is a given tree. Check the balance factors. 0, 0, 0, 0. Then this is 1 and 0, 1. This is 1 minus 1, 0. This is 1, 2, 1, 2. So 0. This is 0 and 1 minus 1. 1, 2, 3. 1, 2, 1. So everything is perfect. It's a balanced AVL tree. Now let us insert a key 27. Key 27. Start from here, search for a location for 27, right? Search for 27. If not found, insert it. 27 is smaller, move this side. 27 is greater, move this side. 27 is smaller, move this side. 27 is greater, it's not there, so insert. When 27 is inserted here, now balance factors will update. This is 0, this is minus 1 because 0 minus 1 is minus 1. 1, 2 and this is 1, so this becomes 1. This 1, 2, 1, 2, 3. So 2 minus 3 becomes minus 1. And for this one, 1, 2, 3, 4, 1, 2. So this became imbalance. This node became imbalance. 2 is the balance factor, so the node became imbalanced. We have to perform rotation on that one. So which rotation we should perform? Check the direction of insertion. This is newly inserted node. Left, right, left, right. LR, LR. No. Just we have to check with the 3 nodes. It went on the left hand side and then right hand side. Right. See, this 27 went on the left side, then on right side, then below that where it has gone, we don't know. We are concerned about only these 3 nodes because this node became imbalanced. So from that point, just 3 nodes in the direction of insertion. So this is LR rotation. So we know the direct answer, so I will directly rotate this one. So 30 will go to 40 at the place of 40. 40 will move on the right hand side, and on the left hand side 20 remains as it is. So let us finish these extreme left 10 and 5 as it is. On that side we have 50 and 60, they are as it is, 50 and 60. Then 30 has become a new root. So what about 25 and 27? They remain on left hand side only. So 25 will be as a right child of this one and its right child is 27. Then 35 will remain on the right hand side only, right subtree only. So this will become a left child of 40, 35. It will become a left child of previous root. So this is a balanced AVL tree. Let us check the balance factors and find out. 0, 0, 0, 0. This is 1 minus 0, 1. This is 0 minus 1, minus 1. This is 1, 2, 1, 2. 2 minus 2, 0. This is 0. This is 0 minus 1, minus 1. So this is 1 minus 2. So this is minus 1. This one, 1, 2, 3. Or you come this way also, 1, 2, 3. And 1, 2, 3. 3 minus 3, 0. It is balanced. So I have shown you formulas for LL and LR. RR and RL, I hope you have understood. So I don't have to show them. Alright. So that is a student exercise. So you prepare the formulas for them. You work out and prepare the formulas. So next we will take few keys and we will see how a AVL tree is generated. So that I'll explain you in the next video. In this video, we will write a C language program for generating AVL tree. So we will create a balanced binary search tree, that is AVL tree, by inserting the elements by performing rotations. So let us create a project and call the project as AVL Trees as a C language program. So let us create this one. Yeah, let us start. See, the first thing I should define a structure node for a tree. So in this one, we will have a pointer to a left child, that is struct node star L child, then integer data, that is the key element, then struct node star R child. Then for AVL tree, we should maintain balance factor for every node. So balance factors are calculated by the height of a tree, that is height of a left subtree minus height of right subtree. So here we will maintain height for every node. So in this way we can get the height of left subtree and right subtree and calculate balance factor. So yes, this is height. So I am introducing one data member, that is height of a node. Then I should have a pointer for a root node of a AVL tree. So I will directly declare a pointer here, that is a root, and I will initialize it to null. Then now we should perform insert. So for insertion, already we have written a function, that is a recursive function for inserting in a binary search tree. It will be almost the same function, just we will say take care of height, and if it is becoming imbalanced, we perform rotations. So I will copy the code for insert from binary search tree. So already we have seen that function, that same function I will copy it here. Yes, here is a function for recursively inserting in a binary search tree. I'll give a gap. So now you can see the complete function. This was the function we have written. Now while insertion, we have to take care of one thing, that we should also set the height. And we know well that in binary search tree, always a element is inserted in a leaf node. So when it is on the leaf node, then the height of that node will be 1. So inside this recursive insert, this is the place where I am creating a new node and inserting it. So after setting key, I will also set the height, that is at 1. See, one thing, if you remember, we have discussed the height. If there is just one single node, then the height is 0. But I am taking it as 1 onwards. Or else you can make it as 0 also. That's your choice. So I am starting height from 1 onwards. See, for example, I'll show you. See, there is suppose only one single node. Then height is 1. Then if it is having a child, then the height of a tree is 2. I'll be taking it as 2. This is 1 and this is 2. Right? We learned that we can start from 0, but here I am starting from 1 onwards. Okay? So if there is a single node, then its height will be 1. So then obviously the height of this one will become, from here, from the beginning, it will become 2. So if there is a single node, then the height will be 1, and then above this one, this node is there. So the height from here to here is total 2. So for this node, I should say the height from here is 2. This is the one thing. Then second thing, for every node, I should update the height. So recursively it is calling. So in recursion process, at the returning time, see this, all that calls, recursive calls are over. At the returning time, I should update the height of every node. So P's height, that is height of every node, should be equal to the maximum height of left subtree of right subtree. Whichever subtree's height is greater, that height we should take. So I have to check the left subtree height as well as right subtree height and take it, and I should take the maximum one. So for that, I should write down some code here. Instead of expanding the code here itself, I will write a function above here for calculating the height. So that function, I will directly use it here. Let us call that function name as node height. So I will call it as node height, height of a node. So for node height, I should send a pointer p. Then I will write on a function for finding the height of a node. So here above this R insert, I will first of all write a function for finding the height. So function node height, and it should take a struct node pointer. Then here I should check. I should find out the height of left subtree and also height of right subtree. And for the height of left subtree, I should check that first of all p is not null. Yes, p, as well as p's left child is there. P's L child. If it is there, then I should take the height of P's left child. Otherwise, the height should be taken as 0. Now, same way, I should also take height of right child. That I will copy this one and paste it here. Only the difference is it is for right child. P is our child, then this is our child's height. Then after this, whichever is greater, in that I should add 1 and set the height of P. So here directly I will write down in return that if HL is greater than HR, then return HL plus 1, otherwise HR plus 1. That's it. So I should check the height of left child and the height of right child, and in that it will be plus 1. Just I'll show you. See, suppose in this tree, this is P. I want to know the height of this one. So height of this should be 2 and the height of this should be 1 because there is only one node and these are two nodes in the height of 2. So P's height should be whichever the value is greater. 2 is greater, so plus 1, 3. So yes, height of P is 3. That is 1, then 2, then 3. So this is how I am comparing and setting the height of P. So here, whatever the height of node is sent by the function, I will take that in the P. So in this way, I'll be updating heights of every node. That's all. Till here, I have completed the code. So what I am doing is, after inserting, at returning time, I am updating the heights of each and every node. Now here I should write on the code for performing rotation. So for performing rotations, I should check the balance factor of each node, then perform appropriate rotation. So for this, I should know the balance factor of node P. After updating the height, I should know the balance factor of node P. I will write down the rotation function for two cases, that is LL and LR, then remaining two are similar only. So let us write down the function. So first of all, I should have a function for finding the balance factor. So here I will write a function for returning balance factor. Let us call the function name as balance factor. Balance factor of struct node. I should take a node and find its balance factor. Now, balance factor is height of left subtree minus height of right subtree. So first of all, I should know the height of left subtree. So the height of left subtree is this one. I can copy this code, and the height of right subtree is this one. Already I have used it here. So copy these two things. Then, now I should return height of left subtree minus height of right subtree. Yes, HL minus HR. So the code is similar to finding the height of a node. There we were adding 1, but now we are subtracting height of left subtree minus height of right subtree. Now here I should check in. Now back inside this recursive insert function, see, till here we have already seen just new line. This is the only new line I have added. Now let us write down the code for checking balance factors and deciding whether to perform LL or LR. So let us start using that balance factor and perform rotation. So if the balance factor of a node, that is balance factor of P, if it is equal to 2, means the node is imbalance. Then it is imbalance on which side? Left hand side, because its balance factor is positive 2, that is plus 2. And I should check the balance factor of left subtree or the left child of a P. So I will call balance factor of P's left child. Here is balance factor small a, and if it is equal to 1, means it is on the left hand side. So I should perform LL rotation. Yes, I should perform LL rotation. So I should call a function for LL rotation. So this logic I have to write down separately. This will be more than one statement. So let us make it as a function. So I will perform LL rotation upon P. And also I should return whatever the address that I am getting. Then similarly, I should perform all type of rotation. So I should check the balance factors and perform rotation. So I will write down rest of them. So I will copy this and paste it here. Now if the balance factor is true and the balance factor of its left child is -1, then I should call LR rotation. Then else if the balance factor is -2, that is it is negative, so it is heavy on the right hand side, then the balance factor of right child I should check, and if that is also -1, then it is heavy on right, so I should call RR rotation upon P. Then at last I'll copy this and paste it here. Now this is for the right child and the balance factor is -2 and the balance factor of right child is 1. That is heavy on the left hand side, so I should call LR rotation. Then I will implement all these functions and show you how these rotations works. So first let us write LL rotation. So here above this insert function I will write down LL rotation. So function will return a pointer to a node and let us call it as LL rotation. This is the function already we are using there. It will take a pointer to a node struct node P. Now how to handle this one? Let us check. So I have an example diagram I will show you there. So rotation is being performed upon node P. Let us see. See, suppose this is P, this node is P, and the rotation, that is LL rotation, is performed over this one. So what are the changes I have to do? I should make this node, that is left child of this P. So let us call this as PL. So this PL should become root and its right child should become, that is PL's right child. So let us call it as PLR. Let us call it as PLR. P's left child and right child should become a left child of P. So the after rotation, the nodes should look like this. I will draw them. This should be P and this should be PL and this should be PLR. So I can use 3 pointers or just by using 2 pointers I can do. But let us make it simple. I will take 3 pointers. Already P is pointing here on this node, upon this node. So I'll take PL and PLR and I will modify these. Now what about the height? See, the height of this PLR remains same because height we are counting downwards, so it will remain same only, and the height of a PL and P will change. So we will calculate it. So let us take 3 pointers and make necessary assignments. So what are the changes I have to do? P's right child should become P. So this is coming on the right hand side. Then the P's left side should become PLR. These are the 2 assignments I have to make and update their heights. So first of all, let us take these 2 extra pointers. Let us take struct node PL, that is P's left child. Then struct node PLR, that is PL's right child. So PL's R child. Yes, perfect. Now what are the assignments I have to make? PL's R child should be made as P. Yes. Then the P's left child should be made as PLR. Okay. Then I should modify the height. I should find out the heights of P and PL because PLR remains same. So let us call function that is node height and change the height of P. P's height is assigned with node height from P. Then PL's height I should change. PL's height should be changed as node height from PL. That's all. Then at last, if suppose the rotation was performed about a root node of a tree, means if this P was equal to root, means if this root was equal to P, means root and P are same, then root should be changed to new node, that is new root, that is PL. That's all. After this, say return PL, that is the new root. That's all. This is LL rotation. Yes. Now let us check by inserting few nodes and see whether automatically this LL rotation will be performed upon a tree or not. So here inside the main function, I'll be calling R insert. So first of all, I should say root assign R insert by passing root and the key is 10. Then R insert root and the key is 5. This will come on the left hand side. Then R insert root, then 2. So this will be on the left's left. So if I draw the diagram and show you, this is how the tree will look like. So this will be imbalance and the rotation should be performed over this 10. So who should become new root? 5 should become new root. Let us check whether it works. Here I will put a bookmark and run and show you. Oops, there are warnings because I have not implemented rest of the functions. So I'll make them as comments. Okay, instead of comments, I'll write down dummy functions. See, for LL rotation also it's giving a error because in LL rotation I have taken a pointer. Yes, LL rotation R is not capital, R is a small. So I have changed that one. Then rest of the functions I'll just write down dummy functions so that it's doesn't show any warning. So this is one more, and this I will call it as LR rotation. Then one more, and this I will call it as RR rotation. And one more, this I will call it as. Then each function I should write on something, so I should return something, otherwise it will give an error. The functions are not returning anything, so write return null for each three of these functions. I will write on null for all of them. Now let us compile and see if there is any error. I will remove it. There is no error. Now let us see the node structure, that is tree structure formed here. Let us expand this. Oh, root is 5. See, root was 10. I have given 10 here. But here you can see that root is 5. Then its height is also 2. And its left child is 2. Yes, perfect. And the right child is 10. Yes, rotation is perfect. That's all. I'll remove the breakpoint. Now I have to show you one more rotation, that is LR rotation. Now let us implement LR rotation function. I'll expand this function. Here I will write on the required code. See, for performing LR rotation, what are the things that we require? Let us look at it. I have an example. See, suppose this is a tree and this is P upon which we have to perform LR rotation. So we need this node, that is P's left child, and also we need P's left child's right child. So this is PLR. And using these three nodes, I have to make some necessary changes. What are the changes I have to do? So this root will be PLR. PLR will become root. P's left child, right child. Right? And its left child remains, that is a PL. It will be PL only. And right child will become P. Right child will become P. Then the left child and right child of PLR will be given to right child of P and the left child of P. So total 4 assignments I have to make. So let us perform this. So for this I will take 3 pointers, that is struct node PL, that is P's left child. So let us take P's left child. Then struct node PLR, that is P's left child, right child. So here PL's R child I will take. Then I have to perform necessary changes. PL's R child should become PLR's left child. P's L child should become PLR's R child. Then PLR's left child should be made as PL. PLR's right child should become P. So total 4 changes I have done. Then let us see whose height will change. So this PL's height I should calculate, and P is also a height I should find out, and then I can also find out PLR's height. So I have to find out the height of a PL. So PL's height is node height of PL. Then same way P's height also I should find out. Node height of P. Then I can find out PLR's height. That's all. All the heights are updated. Then I should return PLR. This is the new root. So this I will remove it. And at last I should check one more thing, that if P is equal to root, means root was actually equal to P. So if root was P, means now it has become a new root. So root should be what? PLR. That's it. So how we should construct a tree, I'll show you an example diagram. Then based on that we will construct a tree. So for that I will take some values, like here I will take the value that is 50, root is 50, let us take it as 50, then left child as 10, okay, then right child as 20 I will take. So the result should be such that 20 is in the root and the left side is 10 only, and the right side should become 50. So let us give these values and check. Here already I have a breakpoint, so here I'll give the root value, that is 50, and the left child is 10 and the right child is 20. Now if I run this program under debug mode, let us see what happens. Yeah, root is 20 and its left child is 10 and the right child is 50. Yes, perfect. Rotation is performed. That is LR rotation is performed. See, we are getting the same thing, that is root is in 20 and the left child is 10 and the right child become 50. So LR rotation was also working perfect. Then remaining, that's all. I'll stop here. You have to write down other two rotations and check them. Just instead of left and right, you have to just switch their names. That is, left should become right, right should become left. And already I have written the code for checking balance factors and calling the respective functions. So you can use this one. That's all in this video. In this video, let us look at how to create a AVL tree. I already have set of keys here. Using these keys, I have to insert them one by one and generate a AVL tree. The process is same as binary search tree, but also we have to calculate balance factors. If any node is becoming imbalanced, then we have to balance that node. So let us start by inserting these keys one by one and generate AVL tree. So first let us insert 10. Insert 10. So 10 is the only key now. So what's the balance factor of 10? 0. Now insert the next key, that is 20. I will insert 20 also. So 20 comes on the right hand side because it's greater than 10. So 20 is the new node. If I recalculate balance factors, then this is 0 and this is -1. Is it balanced? Yes, 0 and -1 are balanced. Now let us insert one more key, that is 30. 30 is also inserted. So 30 is greater than 10 and greater than 20. So it gets inserted here. Now I have to recalculate the balance factor. So this is 0 and this is -1 and this became -2. So this node became imbalanced. So which imbalance? The direction of insertion is right, isn't it? So this is -2 means it is imbalanced due to right side. And what about its child, right child? That is also minus 1, means it's also imbalance on the right side. So we have to perform RR rotation. So RR rotation we will perform. Then after rotation, what will be the tree? I will draw it here. So this is 20 and this is 10 and this is 30. The balance factors are 0, 0 and 0. This is the result. Okay. This is the tree we got. I was inserting the key. When the tree became imbalanced, one of the node became imbalanced, I have performed rotation. I have adjusted it. So that's how the moment a tree node is becoming imbalanced, we perform rotation and we keep the AVL tree always balanced. Now one important thing I will tell you. Suppose I have not performed rotation over this one. I just ignored it, right? If I ignore it, then even the balance factor may become -3, -4 also if I go on blindly inserting it. So that should not happen. So you should never get balance factor more than 2 or less than -2, right? So you should never get -3 or -4 like this. That's what. Always balance the tree whenever any node is becoming imbalanced. Let us continue. I have to insert more keys. So here I will insert 25. Now this is the resultant tree I have. So I will insert 25, right? Here I have inserted 3 keys. Now 25 is greater than 20 but less than 30. So it comes on this side, 25. What are the new balance factors? This is 0 and this is 1. And this is 1 and 2. So this is 1 minus 2 is -1. Now the next key is 28. 28, insert 28. 28 is greater than 20, less than 30, greater than 25. So it comes here. Let us see balance factors. This is 0 and this is 0 minus 1. So -1. And this is 1, 2 minus 0. So this is 2. This one is 1, 1, 2, 3. 1 minus 3, so this is -2. So how many nodes became imbalanced? 2 nodes became imbalanced. This one is also imbalanced and this one is also imbalanced. Newly inserted node is this one. Then which is the first ancestor which became imbalanced? This is the first ancestor which became imbalanced. Which rotation will perform on that one? Based on this, in which direction insertion is done? Left, right. Isn't it? So we have to perform LR rotation. The other way, what is the balance factor? 2. 2 means it is heavy on left hand side. Then this is -1. So it is heavy on right hand side. So LR rotation we have to perform. So LR rotation upon this one like this and then this one. So this is LR rotation upon this node. Then what will be the resultant tree? This 20 and 10 will remain as it is. They are not touched, they are not modified. Then what about this? As this is LR rotation, 28 will take the place of root, 30 will come on the right hand side and 25 will remain as a left child. So this is the tree after performing that rotation. So what are the balance factors? 0, 0 and this is 0 because these are leaf nodes, and this is 1 minus 1, this is 0, this is 1 minus 2, this is -1. So now again that is balanced binary search tree, that is AVL tree. So till here 28 I have finished. Then 27 is there. So in that tree I will insert 27. Insert 27. 27, where it will be inserted? 27 is greater than 20 but less than 28 but greater than 25. So it comes here on the right hand side of 25. Let us update the balance factors. This is 0 and this is -1. This is 1, 2, -1. So this is 1, 2 minus 1 is 1. This is 0 only. What about this? This is 1, 1, 2, 3. So this is 1 minus 3. This is -2. So that node, root node became imbalanced. This node became imbalanced. So what was the direction of insertion? Right, left, RL, RL. So actually this is the new node inserted, RLR. As I already said, we always perform rotation within 3 nodes or by taking only 2 steps. So RL rotation we have to perform, right? In other words, this is -2, so this is heavy on the right hand side. And its child, if you see it is 1 positive, means it is heavy on left hand side. Alright, so RL rotation we have to perform. RL rotation, when we perform it directly, so this goes into the root and this comes on the left hand side, root comes on the left hand side. So I will draw it here. 25 will move up, so 25 moves up. Then 20, the present root will come on the left hand side. Okay, so 10 will remain its left child only. Then right side it was 28, so 28 will remain its own place. Then 30 was its right side, so it remained its own place. When 25 has become a new root, what happens to 27? Its right child, 27, right child. Right child remains in right subtree only, so on that side only, so it becomes a left child of 28. This one. We have already seen this formula, right? Already have explained you this one. So we have performed RL rotation. So this is RL rotation. Then this is the result of RL rotation. Let us check the balance factors. 0, 0, 0, and this is 1, this is 0, this is 1, 2, 1, 2, so this is 0. As we have performed rotation about this one, so that became 0. Now one last key is remaining, that is 5. Insert 5. So if I insert 5, 5 is smaller than 25, smaller than 20, smaller than 10, so it comes as a left child here. Now the balance factors will update. This is 0, this is 1, and this is 2. And this one is 1, 2, 3, 1, 2. So this becomes 1. So who became imbalance? This node became imbalance. Right? Insertion is done on which side? Left of left. So perform LL rotation. So if I perform LL rotation around this node, then what will be the resultant tree? This is 25 here. This will move up and this will come on the right hand side. So this is 10 and the right side is 20 and left side is 5 only. This is the left child of 10, remains as it is. And the other side, right hand side of the tree remains same. So this is 28 and this is 27, 30. Now balance factors, these are 0, 0, 0 only. These will update 0, 0, 0 and this is also 0. So this is the final tree that we got after inserting all the keys and also balancing it simultaneously. So this is the final AVL tree, right? So this was the first one, then the second one and the third one, fourth, and this is after rotation. This is after rotation, and which rotation we have performed? LL rotation we have performed. Now let us count how many rotations I have performed for generating this AVL tree. 1, 2, 3, 4. 4 rotations I have performed. And in this 4 rotation, this is RR and this is LL. So 2 single rotations. And this is LR and this is RL. So 2 double rotations. So for these keys, total 4 rotations are required. 2 are single rotations and 2 are double rotations. And 7 keys I am inserting. What is the height of a AVL tree? Finally, I got 0, 1, 2. See, this is the minimum height. So that's all. Now, one more thing I would like to show you here. If I am not performing rotations, simply I am creating binary search tree, then what happens? Let us look at it. Let us create a binary search tree for these keys. First is 10. 20 is greater than this one. 30 is greater than 10 and greater than 20. 25 is greater than 10, greater than 20, less than 30. 28 is greater than 10, greater than 20, less than 30, but greater than 25. Here it comes. 27, greater, greater, smaller than this, greater than this, smaller than this. 5, smaller than this. See what is the height. 0, 1, 2, 3, 4, 5. Here the height is 0, 1, 2 and there the height is 5. See the difference. Binary search tree is useful for searching. In this tree, if I search, what is the maximum number of comparisons required? 6. 1, 2, 3, 4, 5, 6. 6 comparisons required. If I am searching for 27, it will be found after comparing 6 elements. Here, if I search any key, maximum how many comparisons? 1, 2, 3. So in 3 comparisons, I can find a key. Here, 6 comparisons maximum. If I am searching for 10 or 5 or like that, then less comparison. But at most, how many? Maximum. So this is having almost maximum height. So that's why if you're making a binary search tree, make it as AVL tree. Try to make it balanced so that the searching time is less. So AVL tree is a perfect binary search tree. Now one more last thing. See, height is 2, but what are the maximum comparisons? 1, 2, 3. So why don't we count height from 1 onwards? So the number of comparisons are exactly equal to the height. I don't have to say height plus 1. I can say height, directly height. So actually height and levels, all these are meant for analysis purpose, right? They are for analysis purpose. So you can start from 0 also, 1 also, that's your choice. So if you are counting height from 1 onwards, that's not wrong. So that's all about creation of a AVL tree, and also I have compared with binary search tree. Then also I have told you that height can also be counted from starting from 1 onwards. So that's all in this topic. Now the topic is deletion from AVL tree. Deletion from AVL tree is the same as a deletion from binary search tree. So I'll just tell you the procedure. First, search for a key that you want to delete. If found, delete it. Then who will take its place? In order predecessor, or in order successor will take its place, right? If you want to learn it, you can go back to deletion from binary search trees and you can watch that video once again. So same procedure is followed. But AVL trees are height balanced binary search trees. And the height balancing is done with balance factors. So if any node is becoming imbalanced, we perform rotations for balancing it. So we have already seen how the rotations are performed at the time of insertion. If any node is imbalanced, then there are 4 different types of rotation. We can perform the suitable one. Now at the time of deletion also, any node may become imbalanced. So if any node is becoming imbalanced, then we need to perform rotation. So what are the types of rotations available? So there are 6 rotations available. Don't panic with these rotations. These are not new. Already in insertion we have seen 4 rotations. 2 were single rotations and 2 were double rotations. That same rotations we perform, but we have given different names. These 6 names are to identify which rotation should be performed out of those 4. So let us look at them. So it will not take much time for me to explain these rotations. So already I have taken some examples. Now through those examples we will learn about them. So first we will learn about these 3 rotations, that is L1, L-1 and L0 rotations, right? So for that already I have examples. Then after that we will see R1, R-1 and R0 rotations. So let us look at this L rotations. First rotation, this is L1 rotation. This is the example for L1 rotation. Now look at this, watch it carefully. Suppose I am deleting 40, this node I am deleting. If this node is deleted, then how the tree looks like? This is how the tree looks like. And the balance factors will be 0, 1 and this becomes 2. So this node became imbalance, right? This node became imbalance. So what is the reason of becoming imbalance? Because we have deleted a node from right hand side, right? Deletion is done from right hand side. So in all these examples we'll be deleting from right hand side only. So it is becoming imbalance from which side? From left hand side. So if you remove something from right side, it will become heavy on left side, definitely. So it is imbalance upon left hand side. Now if you look at the very first child of this node, right, on the left hand. So if you look at the left child of this node, its balance factor is 1. So that's why we call it as L1 rotation. So which rotation we should perform here? Now you know very well that rotation should be performed over this node, right? Over this node, this type of rotation. So earlier we were calling it as LL rotation. Yes, this is LL rotation only, but in deletion we are giving a different name, that is L1. So only the purpose of name is to identify which rotation I should perform, which type of rotation I should perform. So depending on the balance factor of this node, I should perform LL rotation. So the new tree will be this one. So this is a balanced tree, and the balance factors are 0, 0, 0. So first one is completed. Now let us look at the second one, L minus 1. Now again we will delete 40 from right hand side. If I delete 40 from right hand side, then after deletion the tree looks like this. This tree is after deleting 40. Now what are the balance factors? 0, minus 1, and this became 2. So this node became imbalance. So which imbalance? What is the balance factor of its left child? It's minus 1. See, we are deleting from right side, so check the balance factor of left child. It is minus 1. So this is L minus 1 imbalance. So which rotation I should perform? First this one, then this one. So this is LR rotation. It is heavy because of left right, isn't it? Why right? Because this is minus 1. So it is right side heavy. This is left side heavy. This is positive 2. So this is left side heavy. This is negative 1. So this is right side heavy. So perform LR rotation. So this is double rotation. So if you perform this double rotation, then the resultant tree will be 20 will go up in the root and 10 remains on this side only, 30 remains on this side. So this is same as LR rotation, right? But we are calling it as L minus 1. Why? Because this node became imbalanced, its left child is minus 1. The third one, this is L0 rotation. From this again we'll delete this node 40. After deletion, tree looks like this. This is the tree after deletion. Balance factors are 0, 0, 0, and this is 2. Now this node became imbalanced because of deletion from right side, so it is left side heavy. What is the balance factor of its left child? This is 0. Which rotation I can perform? I can perform either L1 or L minus 1. Any one rotation you can perform, you have a choice here. So it means if I perform L1 rotation, then this 10 will move up and 30 will come to the right side, 20 will be on the left hand side of this one, and 5 will be here. This is balance. If I perform L minus 1 rotation, then 20 will go up in the root, then 10 on this side, 5 on this side, and 30 will be moved on to the right side. Any one of these three. This is based on L1 rotation, this is L minus 1 rotation. This is single rotation and this is double rotation. If I check the balance factors, 0, 0, and this is 1 and this is 1. And the balance factors here are 0, 1, 0, and this is also 1. So, but in this one, if you see the root upon which we have performed rotation, that is not becoming 0. Right? It's not becoming 0 because this side was perfectly balanced. Right? This side was perfectly balanced. So when we are trying to balance this one, this is not becoming zeros. Earlier this was becoming 0. This was becoming 0. So that's all. These are the these are the rotations when we are deleting any node from right side. Right? So we have to perform rotation from left side. So that's why these are L0, L minus 1 and so that's why these are L1, L minus 1 and L0 rotation. I hope I don't have to explain you R1, R minus 1 and R0 rotation. Those rotations will be similar to these, just it's a mirror image of these three cases. Deletion will be done from left side and it will be imbalanced from right side. So we balance it. Right? So like here we have LL rotation, there we will have RR rotation. Here it is LR rotation, there we will have RL rotation. And here we will have any of the option when it is R0. So you can try out this one by yourself. So 3 more rotations you can do by yourself. That's all about rotations at the time of deletion. Yeah, the topic is height versus node analysis for AVL trees. Similar analysis we have already done for general binary trees and strict binary trees, and also for complete or strict n-ary trees we have done same analysis. Now we'll do that analysis upon AVL tree. So what we have to do is, if height of a AVL tree is given, height is given, then find minimum how many nodes are possible in that height, maximum how many nodes possible in that height. So AVL tree is a binary tree only, basically. Binary tree, then binary search tree, then it is height balance binary search tree. So basically it is binary tree. So in any binary tree, if height of a tree is given, then maximum how many nodes can be there? 2 power h plus 1 minus 1 nodes will be there. Yes, we know this one. So I don't have to explain that one. So this is coming from binary trees, right? So anyway, I will come across this formula once again. Now the question is minimum how many nodes if height is given. So how to get the formula? See, formula by taking the sample values or examples from the observation, you can prepare the formula. So formulas comes from observation. Let us take some examples of some heights of AVL trees, then see how many minimum nodes required, then we'll come up with the formula. So let me show you some examples. First example, let us assume that height is 1. What about height 0? We will start height from 1 onwards, right? So here we will start from 1. So if height is 1, then just one node. I'm not labeling, I'm not putting any values. So how many nodes required? Minimum 1 only. Maximum also 1, minimum also 1. Height is not 0, height is starting from 1. The next, if height is 2, then minimum how many nodes required? 2 nodes. Yes, height is 2 nodes. If height is 3, then the minimum how many nodes? 3 nodes. 3 nodes required. Minimum 3 nodes. No, wrong. This is wrong. Is it a AVL tree? AVL tree means height balance. So if you check the balance factors, this is 0, this is 1 and this is 2. This is not balance. So I need one more node on this side to make it balance. Yes, now the balance factors are 0, 0, 1, 0 and this is 1. Yes, this is balance. That's it. Minimum node means it must be balanced. So minimum how many nodes required? 4 nodes required. So take 4. Then if the height is 4, then minimum how many nodes required? 1, 2, 3, 4. Is it balanced? No. This side I need some nodes. One node, is it sufficient? No, still it is imbalance. One more node, is it balanced now? Yes, that is balanced. What about this node? This is not balanced. Now everything is balanced. Let us check 0, 1, 0 and this is 1, this is 0, this is minus 1 and this is 1. 1, 2, 3, 1, 2. Yes. So total how many nodes required? 1, 2, 3, 4, 5, 6, 7. 7 nodes required. Minimum 7 nodes required for height 4, where the heights are starting from 1 onwards. Then for 5 also I will draw it here. There is no space on that side. If height is 5, then minimum how many nodes required? I will draw it. 1, 2, 3, 4, 5. No, this is not balanced. If you have 5 nodes this side including this one, 4 nodes must be there, then only it is balanced. Okay, 1, 2, 3. Total 1, 2, 3, 4. Yes, perfect. Including that root. Then what about this? For this, including this one, 1, 2, 3, 4 you have. So you should have 1, 2, 3. Now it is balanced. Now here you have 3. So here you should have 2. Balance. Here you have 3. Here you should have 2. Balance. Now this is balance. If you check the balance factors for all the nodes, then the tree is balanced. Total how many nodes are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So minimum 12 nodes are required. Yes. Now we have enough examples for observation and to get the formula. Now I have some set of values. Let me prepare a table. If height is given, then how many nodes for a given height? Let us make it as a function. So if height is 1, 1 node, 2, 2, 3, 4, 2, 2, 3, 4, 4, 7, 4, 7, 5, 12, 5, 12. I'll extend it. 6 and 7. Tell me the answer for these. How I got this 12? Let us observe. 4 plus 7, 11. 11 plus 1. Okay. 4 plus 7 plus 1. Am I getting this value also like that only? 2 plus 4, 6 plus 1, yes, 7. How I got this one? 1 plus 2, 3 plus 1, 4. So it means this one is 7 plus 12, 19 plus 1, 20. Then how to get this one? 12 plus 20, 32 plus 1, 33. Yes. So the formula is number of nodes for a given height is previous two values are added and plus 1. So n of h minus 2 plus n of h minus 1 plus 1 plus 1. Yes, this is the formula. Then for the very first value, I should have two values with me. So when height is 0, answer is 0. When height is 1, then the answer is 1, right? Otherwise, this is the answer. So when height is 0, answer is 0, height is 1, answer is 1. Otherwise, this is the formula used. So formula for minimum is this one. And for this is the table. So minimum nodes can be obtained by this formula. So I should write down this formula here for minimum nodes. So I will not write the formula. I will say look in the table. So for minimum nodes, look into the table. So if height is 5, minimum 12 nodes, height is 6, minimum 20 nodes, like this. Then there is one change here. See, I started height from 1 onwards. When I have only one node, height is 1 onwards. So if height is 3, then 7 nodes. These are 7 nodes, right? This height is 3, 1, 2, 3. So maximum 7 nodes when the height is 3. So this maximum nodes formula, we will get 2 power h plus 1 minus 1, but now we will have just 2 power h minus 1 formula because the height is starting from 1 onwards. So maximum nodes formula is this one. So if I add these 1 node and these are 2 nodes and these are 1, 2, 3, 4 nodes, so 2 square. So this is 1 plus 2 square is equals to 2 cube minus 1. 2 cube minus 1 is what? 8 minus 1, that is 7. So yes, we have 7 nodes. So this is 2 cube, height is 3. So just 2 power h minus 1. Now we have the formulas. If height is given, then minimum nodes and maximum nodes. We need another formula. If nodes are given, then what is minimum height and maximum height? So let me write down, I'll remove this. If n nodes are given, then find minimum height and maximum height. So if you remember in binary trees, what we did is, we converted this minimum formula to maximum formula and maximum formula to minimum formula. We'll do the same thing here. So we don't have to do any analysis. See, maximum nodes are n equal to 2 power h plus 1 minus 1. Then minimum height will be h is equals to n plus 1 log base 2. So log base 2 n plus 1. No need of minus 1 because in power we don't have plus 1 here. So log base 2 n plus 1. Then what about maximum height? This comes from minimum nodes formula. There it is, look on the table. So here also look in the table. You have to look into the table. How? Let me give an example. If I have 12 nodes, then what is the maximum height? 5. If I have 13 nodes, 13 is less than 20. So this side only, here only. 13 nodes also 5. 15 nodes, 5 only. Maximum height, 5. 19 nodes, height is 5 maximum. See, these are minimum nodes required for getting this height. Now I have 20 nodes. Okay, maximum height is 6. Maximum height is 6. So from this 12 to 19, maximum height is 5. And 20 to 32, maximum height is 6. So you can look into the table and you can read it this way. Instead of from height towards node, you have to see from node towards height. That's it. So you can find out. So you have to practice this little bit, put it by yourself on using pen and paper, then you will remember everything, right? Just practice it once, you will remember it. So we have done in-depth analysis of AVL tree. Now one last thing. See, this formula for minimum number of nodes formula, right? This one, minimum number of nodes formula. Actually, this formula is meant for this one and also useful here. Height is given, nodes, minimum nodes formula. This formula is same as Fibonacci series formula. Yes. Fibonacci series is famous for being a balanced series. Balanced series. You take any two terms of Fibonacci series like Fi and Fi plus 1, any two terms. For example, F10 and F11, two terms. Then F11 by F10 if you do, or Fi plus 1 by Fi if you do, ratio will be 1.6. Approximately, not exactly. It may be 1.59, it may be 1.57 also. You should accept it as 1.6, or it may be 1.6162 also. Approximately 1.6. So any two consecutive numbers, if you take the ratio, it is 1.6. So Fibonacci series is believed to be a balanced series. So this formula is matching with Fibonacci series, means AVL trees are also balanced. This is a proof that they are balanced, because so their formula for node versus height is same as Fibonacci series. Then one last thing, minimum height is log n plus 1 base 2. Maximum height, look into the table. Table is from the formula. So from this formula, can't I calculate height? Yes, approximately if you calculate from this one, there is a derivation. If we derive that and get the answer, then approximately it is equal to 1.44 log base 2 n plus 2. If you use this formula and convert it in terms of log n, we get this answer. So minimum height is also logarithmic, maximum height is also multiple of logarithmic, but logarithmic only. So AVL trees height is always in terms of log. That's it. This is enough with the analysis of height versus nodes.